The formal mathematical structure of quantum mechanics can also, of course, be applied to determine the statistics, perhaps, of measurements made of quantum mechanical systems. These notions of statistics appear a lot in the context of uncertainty, for example, variance, and the overall average outcome, the expectation value. So let's consider how the formal mathematical structure of states in a Hilbert space can be used to determine statistical properties of quantum mechanical systems. What we're talking about here is some observation. So consider just some generalized observation, meaning I'm talking about some observable Q as represented quantum mechanically as an operator, Q hat. We've talked about, over the last couple of lectures, eigenvalue problems. Q hat applied to some state gives me Q, the eigenvalue, multiplied by that state. And we've talked about the results of these eigenvalue problems. Either we have a discrete spectrum, we get some sort of set of psi sub n's associated with some Q sub n eigenvalues, from which we can construct, for instance, any arbitrary state f, for example, as a superposition of a bunch of stationary states, or a bunch of states here, a bunch of psi sub n's multiplied by some sort of a coefficient. And we can determine that coefficient with Fourier's trick, left multiplying this overall expression by a particular psi sub I. So a sub I is going to be given by psi sub I f, coming from the left-hand side. The sum on the right-hand side collapses, etc. The usual Fourier's trick reasoning applies involving the orthogonality of the psi sub n's. We have this nice set of mathematical tools that we can use. We have a set of vectors that forms a complete basis for arbitrary functions. These are orthonormal basis vectors, basis states, and they can be used to construct anything. We also talked a little bit about what happens if you get a continuous set of solutions, not a discrete set. So let me just write this as some arbitrary psi of q. I'll write this as a state. It looks sort of like a function and a state. Think of this as a state that depends on some continuous parameter q. So each value of q plugged into some general structure gives me a distinct state, and I can think about the eigenvalue as q. Under those circumstances, the completeness of the basis states can be expressed as an integral. So I'm constructing the same sort of general quantum mechanical state as an integral over q of some sort of coefficient. Let me write it as f of q, multiplying this state psi of q. So I have some general function multiplied by some general coefficient, and I'm integrating up if I have some sort of continuous spectrum of eigenstates and eigenvalues. This f of q is determined by Fourier's trick using the Dirac orthonormalization of these sorts of states in much the same way. It's again going to be an inner product of psi of q with the state that we're trying to find, or with the state that we're trying to represent, excuse me. Now, given this sort of mathematical structure, can we discuss the notion of measurement, or some sort of an observation? What happens when we measure q? We've got some sort of device, we've put our quantum mechanical system into it, and it spits out a number. What numbers is it likely to spit out? Well, in the discrete case here, it's actually quite straightforward. You are going to get one of these eigenvalues. This is the generalized statistical interpretation of quantum mechanics. You're going to receive one of the q sub n's in that set of q sub n's. I should probably use a different index here. One particular value from that set, and you're going to get it with probability given by, well, if I get value q sub n, I'm going to get it with probability a sub n squared. So the coefficients that appear in this expansion, this representation of the state in terms of these basis vectors, is really the, well, square root, in some sense, of the probability of receiving each particular eigenvalue. So this is actually quite an interesting statement. When we measure q in a system with a discrete quantum mechanical spectrum, we always get one of the eigenvalues of the operator corresponding to the observable that we measure. And we get that value with probability given by this very simple sort of formula. You can take the squared magnitude of, essentially what you're looking at here is the part of f that is in the psi sub I direction, if you want to think about it. There is, of course, a continuous counterpart to this, but measurements of a continuous spectrum are a little bit more subtle. You have to think about what it means to observe something, and you're never going to, if you're trying to compute the probability of getting, say, exactly 6 out of a continuous distribution, exactly 6 will never happen. You will only get ever numbers very, very close to 6. But you can think about what's the probability that I get some value q in between q0 and q0 plus some dq. So I've got some sort of interval here between q0 and q0 plus dq. If the value that I get falls in that range, then we can represent the probability here. And you'll get it with probability given by the magnitude of f of q squared multiplied by dq. So this f of q, this coefficient that we determine as the result of an inner product with our sort of basis and the function that or state that we're trying to represent, can be used as a probability. This is the sort of thing that we're talking about when we talk about the squared modulus of the wave function as a probability density. The wave function psi of x is really the result of some sort of inner product between eigenfunctions of position operator, which are Dirac delta functions, as applied to the state that we're trying to represent. So that's where the probability density comes from. Now, this is not so much a mathematical result that can be proven. These sorts of, you'll always get an eigenvalue and you get some sort of a probability, or you'll always get some sort of a continuous value, some sort of a value with this sort of probability. Those aren't mathematical results as much as they are sort of axioms of quantum mechanics. This is a generalized statistical interpretation that takes us beyond the notion of the wave function as something that gives you the probability density of position measurements, meaning the probability density of where you're likely to find the particle if you observe the particle, meaning observe its position. So these sorts of probabilities are, of course, going to be useful in the context of computing probabilities, but in order for them to be useful in computation of probabilities, we first of all have to have some sort of normalization. Now, you can think about normalization of a wave function or of a state in the context of these vectors in the Hilbert space as the inner product of the state with itself must equal 1. Now, if you think about that in the case of a discrete spectrum, this state f can be written as the sum of some a sub n times some psi sub n, meaning if I'm working with some set of psi sub n functions, some sort of a basis, I can figure out the overall, I can figure out these coefficients and determine the overall state that I'm trying to represent. If you look at this inner product in this context, you're going to have, well, it's an infinite sum and an infinite sum. So I've got some sort of a sum over n of a sub n star, psi sub n on the left, and some sort of an infinite sum over n, or sorry, I should use m, different index, of a sub m, psi sub m. And if I distribute these two infinite sums together, I'm going to get psi n, psi m terms, and psi n and psi m, those inner products, obey an orthogonality relationship. I'm assuming these psi sub n's come from the eigenstates of a Hermitian operator. So the orthogonality is going to collapse the two sums together, and I'm just going to have one sum left. I'll get, say, a sum over n of a sub n star, a sub n. And the normalization means psi n, inner product is 1. So my wave functions are gone. So this normalization condition here implies that the sum of the squares of those coefficients in the representation of my state is going to be 1. In the language of continuous spectra, what we're talking about here, again, is an inner product. Inner products you can think of as integrals. So we've got some sort of an integral of some sort of f of q squared modulus dq. This is, again, sort of an addition of all probabilities. What we've got, an addition of probabilities here, a summation of a bunch of probabilities that better add up to 1. This is an integral of a bunch of probabilities that adds up to 1. And this integral comes from the same sort of orthogonality argument as the infinite sums collapsing here. Instead of two infinite sums multiplied together, we would have two integrals, which we could manipulate to get a Dirac delta function in terms of the Dirac orthonormalization of these sorts of basis states, what I wrote as psi of q on the last slide. So these normalization conditions make a fair bit of sense. Probabilities have to sum to 1. We can make some use of that. Another situation where these probabilities are useful is in the computation of an expectation value. So say I want to compute the expectation value of some arbitrary operator q. That, in the language of these linear operators, is f inner product with q times f, q operator acting on f. So here's my arbitrary state f again, and q being applied to f. So again, I can make these sorts of infinite sum expansions, sum over n of a sub n star, psi sub n, multiplied by an infinite sum over m of a sub m times q acting on f. Sorry, not f. Once again, psi sub m, coming from this same sort of expansion of f and the expansion of qf. So the expansion of qf is going to be q acting on the infinite sum, and I've distributed q into that infinite sum, acting on each individual term. Now, q acting on psi sub m, that was my original eigenvalue equation. Q acting on psi sub m is simply going to give me q multiplying psi sub m. So in the case of calculating the expectation value of some general operator, when you have your general state represented in terms of eigenstates of that operator, is actually quite simple. Again, we're going to get psi n and psi m when I distribute these two sums together. You're going to have a sum over n and a sum over m. I'm going to have an a n, that looks a little bit like a w, a n star, and an a m, and a q. This is technically going to be q sub m, associating psi sub m with q sub m was part of the definition of these psi sub m's. And I have a psi sub n and a psi sub m, which again, I can say this is some delta n m, which collapses my sum down. And what I'm going to get in the end is a sum just over a single variable, let's say n, times the squared modulus of a sub n times q sub n. So this, if you look at it from the perspective of statistics, this is a weighted average. These are the probabilities associated with each observation, and these are the values that are associated with each of those probabilities. You can do the same sort of thing within the context of a continuous spectrum. Under those circumstances, you're going to have, I'll write it out under these circumstances, the expectation value of q for a continuous case is the integral from minus infinity to infinity. Let's say I've got dq, right, so I'm constructing an integral representation of f. So let's say that's going to be an integral over q1, f of q1. I have to complex conjugate this. So this is my coefficient from the integral, from the representation of f complex conjugated. And then I've got my psi of q1 actual function. And definitely running out of space here. Shift this to the left a little bit. And that whole thing is going to be multiplied by a similar looking integral, except this time I'm going to be representing q applied to f. So this is going to be an integral dq2 to use a different variable. I'm going to have a coefficient f of q2, again appropriate for representation of my state. I'm going to have my operator q multiplying my psi of q2. And close my state and close my parentheses off screen. Hopefully that's reasonably clear in terms of at least my handwriting. This is a representation of this, and this is a representation of q applied to that. You can make the same sort of arguments here. Q applied to my state is going to be q2 in this case times psi of q2. That's my eigenvalue operation. And then I have the same sort of double integral becoming a delta function sort of thing as I had a double sum becoming a Kronecker delta over here. So this is going to give me rearranging the order of these integrations a little bit. Integral minus infinity to infinity dq1, integral minus infinity to infinity dq2, and then I've got an f star of q1 and an f of q2 and q2 and an inner product of psi of q1 and psi of q2. It's subject to these Dirac orthonormalization constraints that we have to have in order to make continuous spectra really make any sense. This is going to be a Dirac delta function of q1 minus q2. Applying that Dirac delta function in this integration means I can do one of these integrals, and what I'm going to get is the value of the integrand such that, or that occurs where the argument of the delta function is 0. So if I'm doing the integral dq2, I'm going to get the value where q2 has become q1. So all you're going to be left with is a single integral, minus infinity to infinity, dq1, and I've got an f star of q1 as before, and an f of q, not 2 anymore, excuse me, f of q1. This q2 becomes q1 is basically the whole point of applying the delta function. This is the result of doing a delta function integral. I've also got that q1 laying around from before, and that's it. That's all there is to it. So this, getting a little cramped in the right, is the integral from minus infinity to infinity of that squared modulus of f of q dq multiplied by, sorry, not dq, let's say multiplied by q integral dq. So this is the same sort of expression here as you have here. So squared modulus times the value, squared modulus times the value, properly normalized, given the Dirac orthonormalization and the Kronecker delta sort of orthonormalization of these two sorts of sets. Either we have a discrete spectrum, in which case things are infinite sums, or we have a continuous spectrum, in which case things are integrals. So that's what your expectation values are going to look like. They're going to be sort of weighted averages with sums or weighted averages with probabilities. Or, yeah, with continuous functions as computed in integrals. You've seen expressions like this before in, for example, the computation of the expected value of the position operator. This is going to be an integral over position multiplied, an integral over position multiplied by the position multiplied by, sorry, this should be squared, the squared magnitude of the probability density, or of the wave function, f of x. Now, of course, all of this is expressed in terms of some general operator q. So let's do an example. Let's think about measuring the momentum for the quantum harmonic oscillator ground state. Now, measurements of momentum means we're talking about the momentum operator. We know we're always going to get one of the eigenvalues of the momentum operator, so we have to, in principle, solve the eigenvalue problem. Momentum operator applied to some arbitrary state gives me the momentum, the number, multiplied by the state. And solving that eigenvalue problem is something we've done. You end up with something like e to the I px over h bar divided by square root of 2 pi h bar, I think, goes in the denominator as well, associated with eigenvalue p. So these are my eigenstates expressed as wave functions, and these are my eigenvalues of those wave functions. Now, we've talked about these things before. This was e to the I kx over root 2 pi, and this was k h bar. How can we determine, for example, what the probability distribution of momentum measurements is going to be for a particle prepared in the ground state of the quantum harmonic oscillator? Well, we're going to get some value p, and we're going to get it with probability given by the magnitude of some function f of p squared. All right? We're not going to get p, we're actually going to get something between p naught and p naught plus delta p. Running out of space here. But the language sort of makes sense. I have some sort of a probability density multiplied by the size of the interval over which I am accepting values of p from p naught to p naught plus dp. That's my sort of probability density. Now, within the language of the linear algebra that we're working with, this function f of p is going to be that psi of p function. Think about that as the complex conjugate of this, multiplied by psi 0. Psi 0 being the ground state of my quantum harmonic oscillator. And you can write out this inner product in terms of wave functions, if you know what these things are. Minus infinity to infinity. I'm integrating dx. And I have my psi sub p on the left, meaning complex conjugated. So this is going to be e to the minus I p x over h bar divided by root 2 pi h bar. And then I have my quantum harmonic oscillator ground state, and we found that in a variety of ways. It looks something like m omega over pi h bar raised to the 1/4 power times e to the minus m omega over 2 h bar x squared. So I have an integral dx of e to the minus x squared and e to the ipx. We've done this problem before. This is computing the Fourier transform, essentially, of your ground state. This Fourier transform is essentially a special case of the sort of transforms that we are making when we compute the sort of coefficients that appear in the expansions or representations of some arbitrary state in some arbitrary basis. In this case, we're working with the eigenstates of the momentum operator. We could also be working with eigenstates of the kinetic energy operator or eigenstates of any other Hermitian operator. They're all going to form a complete orthonormal basis for which these sorts of probability calculations work. So this integral is doable. Not all that difficult. You end up with another Gaussian just as a function of momentum. It's a sort of closed form mathematical expression. So to check your understanding of these sorts of probabilistic interpretations or these probabilistic contexts, the results of, or as they result from the linear algebra in quantum mechanics, suppose you're considering a particle in a box. So we're solving the time-independent Schrödinger equation for the Hamiltonian, which is an eigenvalue problem for the Hamiltonian operator. We get a set of stationary states and a set of eigenvalues. Now suppose I'm telling you that some arbitrary state psi is prepared in this superposition of psi 1 and psi 2. Answer these questions. If you measure the energy, what's the probability of observing one of a couple of different energies? Double check that this shouldn't be f, sorry. I don't know why I always manage to make typos in these check your understanding questions. This should be psi. Is the inner product of psi with itself what you expect it to be? Does it make sense? And suppose I had some general observable with eigenvalues and eigenvectors such that I have some eigenstate G7 which gives me eigenvalue Q7. If I observe Q, write down an expression for what I would expect in terms of the probability of getting Q7 as a result of that measurement. So that's a bit on the statistical interpretation of the formal mathematical structure of quantum mechanics. This basis allows us to construct probabilistic interpretations of way more than just position and momentum. And we'll continue on along those lines far more later on in the rest of the course. Sort of like a function and a state. Think of this as a state that depends on some continuous parameter q. So each value of q plugged into some general structure gives me a distinct state, and I can think about the eigenvalue as q. Under those circumstances, the completeness of the basis states can be expressed as an integral. So I'm constructing the same sort of general quantum mechanical state as an integral over q of some sort of coefficient. Let me write it as f of q. The formal mathematical structure of quantum mechanics can also, of course, be applied to determine the statistics, perhaps, of measurements made of quantum mechanical systems. These notions of statistics appear a lot in the context of uncertainty, for example, variance, and the overall average outcome, the expectation value. So let's consider how the formal mathematical structure of states in a Hilbert space can be used to determine statistical properties of quantum mechanical systems. What we're talking about here is some observation. So consider just some generalized Fourier's trick reasoning applies involving the orthogonality of the psi sub n's. We have this nice set of mathematical tools that we can use. We have a set of vectors that forms a complete basis for arbitrary functions. These are orthonormal basis vectors, basis states, and they can be used to construct anything. We also talked a little bit about what happens if you get a continuous set of solutions, not a discrete set. So let me just write this as some arbitrary psi of q. I'll write this as a state. It looks from which we can construct, for instance, any arbitrary state f, for example, as a superposition of a bunch of stationary states, or a bunch of states here, a bunch of psi sub n's multiplied by some sort of a coefficient. And we can determine that coefficient with Fourier's trick, left multiplying this overall expression by a particular psi sub I. So a sub I is going to be given by psi sub I f, coming from the left-hand side. The sum on the right-hand side collapses, etc. The usual observation, meaning I'm talking about some observable q as represented quantum mechanically as an operator, q hat. We've talked about, over the last couple of lectures, eigenvalue problems. Q hat applied to some state gives me q, the eigenvalue, multiplied by that state. And we've talked about the results of these eigenvalue problems. Either we have a discrete spectrum, we get some sort of set of psi sub n's associated with some q sub n eigenvalues,